This is problem 12.12 from chapter 12, Brigham and Houston Fundamentals of Financial Management, Concise 9th edition. I'm not sure why I'm doing this problem, but what the hey, I like gratuitous, stupid arithmetic. Butler Perkins Company's trying to decide between two mutually exclusive projects. That means they can choose A, or they can choose B, or they can choose neither of them, but they can't have them both. Okay, so each of them costs $67.50 and has a life of 3 years. And then we have annual project cash flows beginning year one. But the problem with the annual cash flows is that there's some variation in there. Project A cash flows, there's a 60% chance that it's $67.50 per year. It can be as low as $6,000, as high as $7,500. That ain't a large window of change. Project B, on the other hand, there's a 20% chance of zero and a 20% chance you'll hit a home run with it. Okay? So Project B is obviously more risky than Project A. Simply, you can intuitively, it's plus or minus $750. Here it's plus or minus $6,000 to $12,000. So the riskier project, 12%, the less risky project, 10%. Okay, so what is each project's expected annual cash flow? Let me add some room in here. I'm going to use the sum product function, equals sum product, and then multiply these numbers times these numbers, and that'll give me the weighted average. Simply multiplies the weight times the value for each of these. Sum product function is a shortcut. And since I set it up here, I can use it over here. Notice Project B has a higher average return, okay? And that's because it's got a higher upside potential. All right, with this one, it could go down 750 or up 750. So the average, 67.50. Here it can go down 67.50, but it could also go up a little over $12,000. So a lot more upside potential, which increases the weighted average expected return. All right, so the problem is part A says what's expected annual cash flow, and that's it for both projects. Now, Project B's standard deviation is 57.98 and its coefficient of variation is 0.76. What's the corresponding numbers for Project A? Well, let me put a little room in here. With Project B, if I take each of the cash flows and subtract the mean from it, and then square it, and then I take the weighted average of these squared deviations, I've calculated the variance. Okay, but I don't really want the variance, I want the standard deviation. So raise that to a half power or take the square root, either way. That's the Project B standard deviation, 57.98. Let me quit showing my pennies. Okay, so I've calculated it for Project B. I'm going to just move this down a hair. and we'll call this the standard deviation. And I want the coefficient of variation is simply the risk, which is the standard deviation, divided by the return. Okay, so, and that's not in dollars, it was actually just a ratio of two numbers. So now those two numbers were given to me in here. They're asked me to calculate them for project A, except that from what I've done here, since I set this up using cell references, I can just copy it over here and it's going to do the same thing. Alright, so take the mean deviation, square them, then take the square root of the weighted average of the squared deviations. That's your standard deviation. The coefficient of variation, risk per unit of return. We can see that project A is radically less risky. So, BPC wants to evaluate these projects using risk-adjusted discount rates. Alright, so they use a weighted average cost of capital for this project, since it's less risky, at 10%, and for this project it's going to be at 12%. Alright, so all I need now is the cash flows so I can calculate the NPVs for these. Okay, so time period 0, 1, 2, and 3. Both are 3-year projects. Each cost $67.50. The expected cash flows coming in, now we don't know, it could be higher or lower, but we take the average as the expected number for each of the years. And there's $76.50 a year for project B. Okay. So to get the NPVs of the projects, I need the present value of the future cash flows, and I'm using the risk-adjusted discount rates. And the initial outlay, so the NPV for project A, the NPV is 10,036. Using cell references, copy all that crap over, and it's actually higher for project B. Project B is riskier, but even after adjusting the weighted average cost of capital for risk, it still has a higher net present value. Okay, so we did these calculations. To get the answers for A. For B, the answer is choose B. For part B, choose B. It has a higher NPV. If I knew that project B's cash flows were negatively correlated with the firm's other cash flows, but Project A's cash flows were positively correlated, how might that affect your decision? Well, Project B, even though it's got standalone risk all on its own, if it's negatively correlated, that means if it turns out to be a real piece of crap, all the other stuff in the business is doing good. If it turns out to be really good, all our other stuff's doing bad. So it's actually going to offset risk. It would actually make Project B more favorable because the results would be counter-cyclical or it'd be a way of hedging the risks that we have. Okay. If the Project B's cash flows were negatively correlated with gross domestic product, it's the stupidest question ever. Okay, well, no more editorializing. Would that influence my risk assessment? Yeah, because then Project B's cash flows, if they're negatively correlated with the general economy, that means that it would help to offset some of the existing company's risk. So, yeah, even though it's got a lot of specific risks specific to this particular project, if those were counter-cyclical to the general economy, then if the general economy was doing good, it'd lower the company's risk. So while it's got a lot of standalone risk, that's what they're getting at with all this other gobbledygook garbage. In the real world, though, it doesn't work like that. Okay. All right, no more editorials.